So maybe if I talk really, really, really fast, we can get this done in under 5 minutes. There is no quiz this week, but I did leave some quick review solutions on there. And notice that everything here we're talking about is concavity. We're going to discuss that here in a few minutes, less than 5 minutes though. What we're learning about is trapezoidal approximations and then the error that accompanies those approximations. Some definite integrals are best found by numerical approximations, and rectangles are not always the most efficient figures to use, which we have found rectangles can tend to have a pretty big error. Using integrals to find area works extremely well, as long as we can find the antiderivative. Sometimes the function's too complicated to find the antiderivative. At other times, we don't even have the function. We only have the measurements taken from real life, like a table of data or something. So what we need is an efficient method to estimate area when we can't always find the antiderivative. So here's an example. We have the function 1/8 x squared plus 1 over 0 to 4. The actual area under the curve, you know to be the integral from 0 to 4 of the function dx. If we evaluated that using the antiderivative, my antiderivative would be 1/24 x to the third plus x, and then I would put 4 into my antiderivative and 0 into my antiderivative and get 20/3, which is about 6.666, okay? If we used LRAM, we would see that I use my left-hand endpoints, and we get an approximate area of 1, 1 1/8, 1 1/2, 2 1/8, which adds up to be 5 3/4, which is 5.75, quite a bit lower than what we had as the actual area because those rectangles are all below. If we used RRAM, on the other hand, you see that we have an over approximation of 7.75. But what if we actually took the average of those two approximations, add them up, divide by 2, and we get 6.75. We're still high, but the error is not nearly as severe as what the error is in LRAM or RRAM. What trapezoids do is they average L and RRAM, okay? So we talked a little bit about trapezoids before when we did our driving problem, but averaging the right and left rectangles gives us trapezoids. You can see that those trapezoids that we put in are much closer to the actual area under the curve. But how do we find the area of a trapezoid? 1/2 times your height, which is going to be 1, times b1 plus b2. So there's our first one. Here's our second one, 1/2 times our height of 1, b1 plus b2. And notice that this b1 is the same as the b2 in the previous example. This b1 is the same as the b2 in the previous example before that. And you can see then that the middle guys are all repeated, but the ends are on their own, okay? So if I would factor the 1/2 out, as well as the height, which is just 1. So if we go ahead and factor the height out, then I would have 1 plus 9/8 plus 9/8 plus 3/2 plus 3/2 plus 17/8 plus 17/8 plus 3. So the middle guys are all doubled. The end guys are on their own. We get 1/2 times 27/2, which is 27/4, which is 6.75, which we found before to be the average of L and RRAM. Here is your trapezoidal rule. H over 2, H is the width of that subinterval, or the height of your trapezoid. We have factored that out, and I'm just going to add together all of those endpoints where I double all of the interior points and I just keep the endpoints singular. So we have y sub o plus 2y sub 1 plus 2y sub 2 plus so on and so forth until we get to the next to last one, 2y sub n minus 1 plus then just y sub n is the last one. So, handy dandy formula. It gives us a better approximation than either the left or the right rectangles. Let's look at the difference between this and midpoint, okay? Because it's a mistake to make that midpoint and trapezoids are exactly the same answer. If I use my midpoints, we can see that we would get 6.625, which is a 0.625% error, which is low on the low end. The midpoint rule gives us a closer approximation than the trapezoids, but it's just in the opposite direction. Because this is a concave up graph, that all those trapezoids are going to be on top or greater than the actual area under the curve. So the concavity will tell us whether or not our trapezoids are an overestimate or an underestimate. If it's concave up, in this case, the trapezoid approximation is going to be over. If we have a concave down graph, it's going to be under. You can see our trapezoidal rule gives us a 1.25% error, which would be high. Midpoint gives us a 0.625% error, which is low. The trapezoidal rule gives us an answer that has twice as much error as the midpoint, but is in the opposite direction. Now, officially done. Have a good night, and we will see you tomorrow. Bye, everybody.